Alrighty, mic check. 1, 2, 1, 2, 3, 4. Blah, 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 blah. All right, that looks good. Okay. All right, intro in 3, 2. Good morning, everybody. It's Monday, April 8th, 2024, and welcome to Game Journal. Oh, nope. Not Game Journal. It's Code Journal, Study Hall Edition. I'm your host, Rhaine Soulforge, but let's not be so formal. You could just call me Rhaine. Ugh. Excuse me, orange juice burp. Hope everyone's having a good Monday so far. Oh, I'm ready for a nap. Try something a little different. Trying to get even if it's a short one, it's going to be an early morning stream. We'll see how it works. Let's get to some coding. Want to start off with blip. Move that over there. No, we're not playing Fortnite, honey. Because Daddy's coding. Dad, get some music going. Gonna start off here finishing up my daily leak code problem. All right. I need this. Don't worry, Michael. We'll go out and see the yeah, we'll see it. I want to keep reallocating the same variables. Same plus favor. Today's question's an easy one. All right, so if all the sits same and students of 0 does not equal. That should be sandwiches. So 0, then run. That's false. It's a simple question today. It's given two vectors, one of students and one of sandwiches. You have two types of sandwiches: circular sandwiches, which is 0, and square, which is 1. And then you have a collection of students. Ooh, that reminds me. I need to yeah, baby. Okay, so we have picky students. Each student prefers a different type of sandwich. So, as the students in line, if the sandwich is currently at the top of the sandwich vector is what they want, they'll take it. They get out of line. If they don't like it, then they'll go to the back of the line, and then the next student comes in and sees if that's the sandwich they like. So I need to see. Students.push backs students of I position 01 entry. I don't want incrementation of I've never compiled this. Let's see what happens. Yay. You can't erase from a... Ooh, that's right. You can't, can you? Vector doesn't have erase. I'm thinking of strings. No, it does have an erase. Well, poopa to do. Vector int constant iterator current equals students dot begin vector constant iterator. We're gonna call this top sando. Spelled that right? Yep. Okay. Vector. We need another iterator. Call this last student. Students got to begin. Okay. Current does not equal last student. All right, so if we're out of sandwiches or there are no students in line, we're going to set our run condition to false and we'll break out this loop. Now we go, okay. Let's take our current. Does it equal the sandwich at the top? If it does, then we're going to increment the number of students that have eaten. We're going to Have a giant brain part. Set current to delete the student. Student got erase. Current. That's what erase does with the iterator. It takes the position that you want to delete. It deletes it, but then it returns the new where you're at in the list. When we do that, we don't want to increment, because then what will happen is we'll skip over values within the vector. That's a no. Alright, so then we need to reset the last student to equal students. I look at students, it looks like students to the new end of the list. Then we continue. Otherwise, we are going to push. Student's going to get out of the line and go to the back of the line. So we want the value of current. And we're going to set current. So we want to get rid of the head. Erase. Erase. Continue. Otherwise. There is a pop, but it's a pop back. And I don't want to reverse this damn list. Ooh, this is gonna run forever though. Hold on. Ooh. So let's do that, then let's this is gonna get expensive real quick. Okay, why are you not formatting properly? There we go. Okay, I can get rid of this. This is going to be slow as molasses. Maybe. Oh, your variables right, Rhaine. Oh, we go out of bounds. Did it again. Plural it, Rhaine. Going out of bounds, aren't I? see if it just doesn't like. Ooh. It does not like. Time limit exceeded because it runs in an infinite loop. Okay. Okay, so I think I know. Yeah. Okay. Think. All right, so we're going to go through the list of students. And actually, let's do our empty list check up here. So if students is empty or Sandos is empty, then we're gonna set run to false, and then we're going to. So why do we? Shush. That's why I'm doing this first and not going straight into Atlas development. My brain is like. All right, so if we're out of that, out of students or out of Sandos, then we just need to stop. So now we're going to go through, and if students sub I equals Sandos sub 0, we have a student who wants that particular sandwich. Going to increment eaten by 1. Under which is erase just gonna grab the front. Okay, so it's just the position you want obliterated or a range. Okay. Just do that. Get rid of that. mean, we're I don't know why I'm dumb. We're only going to look at the top of each stack, so all right. So the student doesn't want the sandwich, so we're going to put not push, erase. Oh yeah, we need to recalculate num students. What? In a minute. Daddy is doing something. Okay. We're gonna need to move that back into this for loop. It might work. If they all like the same thing and student sub-zero does not equal sandwiches, that means we're never going to get rid of that sandwich. Oh, ran out of time. Okay, give me a second, folks. Hello, Rond. I'm gonna butcher your name. Hello, Rond Dij or DJ DJ. Hope you're having a good day. Give me just a moment. I have to go get something for my youngest. Be right back. Okay. Sorry about that. Alrighty. I have a feeling we're running in an infinite loop here. Check to make sure we still have students and sandwiches. Okay, if we do incremented, remove the sandwich, remove the student, take the number of students. Otherwise, the student goes to the back of the line and we remove student from the front of the line. Just do that enough times to get out of the for loop. I wonder if that's what's happening. Let's see what's going on. Size. What I wanted, doop, 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 doop. Okay. Steve. Ooh, excuse me. Sorry about that. All right, so we're cycling through the students and the sandwiches properly. I need a little blank line in between. Don't think we're clearing the Sando queue out properly. Okay, there we go. Yep. What's going on here? Are we getting out of the for loop? Ha ha! So we are getting out of the for loop. The sun. Mm-hmm. Okay, how are you working for one but not? M-O-O-N? Moon? Okay, we're clear to getting in here, and Eaton should be incremented, but it's 0? No. What? Wait. M-O-O-N, moon. Yeah. Yeah. Actually, don't need that. That can't be right. What? I'm streaming what? Okay. Don't worry about it. It's early. Your sister doesn't want to be pestered. Don't worry. She'll check it out with us. No. My God. Okay, hold on. I need to step through this. Run. Yes, please. Blinding everybody, including myself. There we go. And which is a 0, 1, 0, 1. So no, the student goes nope because we're right here. No. We're at 1, 1. Excellent. So we X those out. Now on this sandwich, that becomes, yeah. Excellent. Someone eats that sandwich. We're looking at this one. No. Yes. Now we're looking at this sandwich. Yes. So all 4 eat. Why is it saying it's not? Yeah, because they're placed in a stack. 0 is the top of the stack. Yeah. The moon circles the earth faster than you know. Oh, I'm returning the wrong thing. Too early. I wonder. I don't believe that 0 milliseconds. Okay. Uneaten. That's a weird name for a variable. This still comes back at 0. Oh! Hey, change variable name. You gotta change it everywhere, right? What does it do with that? Come on. Don't mess for me. Now it says 2 seconds. I swear, some days this is a bad metric, given that you have to send your code to a server to be compiled and then ran. So if your network connection gets sluggy, this doesn't stay the same. Yeah, see, now it's back up because I probably had a hiccup between me and the server. Okay. Well, let's open up some Notepad++. Close. New. Send this up to the old GitHub repository. That's weird. How did I lose a curly brace? I see how I lost a curly brace. Rhaine sees now, therefore he's still blind. Alright, so where's my Python? store. April 8th, 2024. Author. Input. And available to the student in queue. The number of students that did not meet. Number of students that have not eaten. Kind of took a bubble sort approach almost. Moving the queue. Okay. If okay. Okay. Stop if there are no more students in queue for sandwiches on the deck. It says student like this type of sandwich. Remove sandwich. Remove student. Update number of students in queue. 1/8. Decrease hungry students or hippos, depending on what you like. Move student to back of queue. Queue. Yes, empty. Or there are no more sandos. Easy. Okay. Save. Code solutions. PPP file. La 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 li da. 1700. Number of students unable to eat lunch because they are too damn picky. Yep. Now we'll just go over into our repository. Upload file. Did I? Okay, I did. 1700. Blop. Four. Roll 8, 20, 24. Easy difficulty. Alright. Okay, well, that's it for our daily leak code. Problemo. Okay, Yubada Tubada. Hey, the permagen's on. Chin. Alright, so we're going down here. Our next topic is vertex buffer layout. But you don't have to get left in the dark. Yes. From all the Xfinities. That's gonna drive me crazy. Okay, there's that. Goes my thing wigging out. Need that. All right, let's minimize that. Open up the VS. Ugh. That's why you need to take a nap. All right. The old Atlas game engine. Yes, forever and ever and ever. Hee. Why am I always grumpy? Oh, because it's early morning and she's grumpy and she's preteen. Explains a lot. All right. No, Rhaine, you're not. I need to set up a virtual machine so I can have a Linux environment for when when I finally get this engine up long enough, I do want to try and make a game engine in Linux. RC. CD Atlas. Okay, NVIM application.cpp. Give it a second. Does it? Ooh, it does. Good. So last time we implemented a vertex buffer class, and now we need to finish. We need to implement our index buffer, which is all this lovely stuff right here. AWV. Go up. No, we want to go up. Platform specific, OpenGL. Okay, so we want to go here, PV, GL. We want to create my brain just went goodbye. OpenGL index buffer .h pragma. Gonna remember my pragma onces this time, folks. It is a Christmas miracle. Nope. Include Atlas renderer buffer.h in our Atlas namespace. I swear, I can type. I don't know. Like my hand gets ahead of my brain. That made no sense. Public. Oh, wait. Chi unrenderer ID public NGL index buffer class. We're gonna take in an array of unsigned integers. Yep, no, that's right, Rhaine. Unbind constant. Okay, that should, for that, we'll go here and make a new file called OpenGL index buffer.cpp. Include our precompiled header, and of course our buffer file. We need to be in our namespace. Okay, so OpenGL index buffer class. The OpenGL index buffer class. We take in our indices and 33. I got a 33-bit. So in here, I probably, oh yeah, probably go in here. TV. I want there we go. All right, so we're going to create buffers. Actually, wait, I do need that. No, wait. Oh, pull out your notepad, Rhaine. Let's try and do GL create buffers. 100% M unrenderer ID. Okay, so we create our buffer. We're gonna bind our buffer. All right, yeah, bind buffer, but this time it's instead of a GL array buffer, it's gonna be a GL element. Array buffer. Renderer. Yeah, it's gonna take forever, Mr. Impatience. And then we're gonna fill our buffer data, date data. Okay, so GL element array buffer. We're going to give it the size of oh no, my brain has just left the building. Hold on. Tab docs.gl. What is it? GL buffer data. GL buffer data. GL4. Specify, no, size. Specifies the size and bytes of the buffer object's new data store. This is EL draw static. Oop, wrong way. We're leaving that alone, but commenting all that out. Let us make a unique pointer to a C index buffer MP dex buffer. That means I no longer need don't need that. That right? Maybe. Then I can come. Oh, I touched my mouse. Bad Rhaine. Yeah, because then we just come down here and we say MP index buffer dot reset new. Oh wait. The and oh god, Rhaine. To create indices. Oh. Okay, close, right. Do I?
Growing a startup is tough.
Here is we actually implement that file, right? That class that we've created. Take this. Okay, what is that? Okay, so create. Called create. Yeah, we haven't sorted this out yet. Create. And then you could also do set a. So we could just insert this case, to be honest. Windows.
So here is okay. Be our delete buffers. Unrender item. All right. Yep, that's right. Okay. Right, find buffer. Unrenderer. Ah! Unrenderer field. How does it feel? Okay. Rhaine buffer. Buffer, I say. Right. Oh. just have to go into buffer.cp. We'll go into visual. Pretty much. Choose Y. That's not what I wanted. There we go. For here, place that with index. Just use then right. Yeah, baby. We'll let you know when it's time. Trust me, the sky will darken.
Lovely. Yeah, that looks pretty good to me. If we go back to the buffer CPP file, you can check that, make sure this all compiles when it does, and then back inside application, instead of having that index buffer as just an unsigned int here, we'll have an index buffer instance here. Okay, cool. And then for that to happen, I need to include buffer, which I already am because I've written one file, which is lovely, nice and easy. We don't need to do this anymore. Instead of buffers and all that stuff and buffer data, we just create indices and then say index buffer dot reset index buffer create indices size, and that's what we need. And size is just the size of indices. Now, actually, this is a good point, right? So the point is, do we actually need size here, or should we rather have count? The reason is that you're specifying U32 indices. You know the size of many, that's minus count. And the other thing we actually do need in index buffer, which is selected, is the count, right? So virtual U32 get count, and right, and this will just tell us how many.
Oh, good point. Yeah. Okay, why would I not allow you to? Okay. No. Okay. Virtual. Count void constant. On the count. That way we can store the count. Unless he just
all of them. So we'll have virtual get count here, which will return a count, and then you can see and count, right? And then
okay, that's yeah, okay. Thought he was gonna do something slick and like calculate it rather than store it, but okay, hold on. Virtual inline? Can we? Maybe.
over here, when we take in the count, we'll set count. So we can do this. And then this becomes count times size of u in 32. Okay, so that's why I like to differentiate between what is in bytes and what is not in bytes, right? If it's count, then it's not in bytes, it's in elements, which means that you need to multiply by the size. If it's size, it's in bytes. Okay, there we go, wonderful. So now back in. U in 32.
In about 4 hours. Well, don't get mad at me. You asked, and I told you. Yeah. I don't know what I just did. Oh, I see what I just did.
Hey Dad, I just
Did you? Okay. Okay.
Okay, so that's why I like to differentiate between what is in bytes and what is not in bytes, right? If it's count, then it's not in bytes, it's in elements, which means that you need to multiply by the size. If it's size, it's in bytes. Okay, there we go, wonderful. So now back inside our application, we create these, and we, instead of having indices in this case, we just have, rather size of indices, we just have 3 because there's 3 indices in here. Yeah, look, I mean,
Yeah. Yep.
I mean, if you wanted this to be automated, you could just do size of. I know some people in play they would do unit 32C, right, like that. That's what I should use here. All right, and then that will give you the actual count, if you really want to do it that way. This will keep the same, and then, I mean, we'll probably need to bind it at some point. If I run this right now, it probably won't give us triangle, because this is a bit suspicious, and unfortunately hasn't been a while since user in jail. But we'll see what we get here, if anything. Okay, so we get nothing, and we get a crash, in fact, inside the driver. Yeah, probably nothing's bound. I mean, we're trying to draw elements here, I bet we've got nothing to draw. So, the other thing we need to do is actually use our, instead of just having 3 hard-coded here, we should get our index buffer and actually get the count. That's why I wanted it here. Okay, so let's fix up our buffers, because clearly I am not as good as I thought. We need to bind our buffer, which I guess means that why to use create, why to use gen, they're the same in terms of buffers. Like textures, you actually specify the target immediately. I kind of maybe thought that it would be like the same here, but I guess not, right?
Dare we try? I'm funny. No, wait, that is right. I like how it's just like, I don't know what a UN32_T is. Because the buffer class is in it. Oh, hey, yeah. Plate form. Yeah. Oh, my typing skills today. Oh, boy, boy, boy. Buffer.h. Look, it knows everything now. Does it not know GL's? Flub up. Yeah, elemental buffer, elemental size of indices, GL, static draw. Did I do it backwards? Oh, look, it compiled. Let's see if we still have our triangle, folks. Yay, it's still there. That's still blue. Well, take a nap and we'll wake you up. Say excellent. Boop, boop. Okay. Oh. Oh, that's what I wanted. Yes. Did it undo my... It did. get those out of sync. I hate when that happens. Blue triangle. Say hello to the blue triangle of doom. Okay. Well, that was all from sorry. Stretch. Okay. Well, that got me all caught up to what I was working on Saturday. So now we have vertex buffers and index buffers. Okay. So now undo that. And we are going to continue on. We're going to learn about vertex buffer layouts. I'm probably going to watch this for about 15 minutes and then I'm going to end the stream. We want playback. This is a 50-minute video.
Abstraction, check out that video if you haven't already. We basically just pulled out a bunch of our code into specific classes that were kind of per render API. So we're dealing with OpenGL at the moment, so we created like an OpenGL vertex buffer and index buffer class that was specifically for dealing with those kind of render API like primitives or just things essentially in a way that was kind of abstracted out where when we kind of call it from our application or from our game kind of code or from our renderer code, it doesn't care which API is actually used under the hood. So definitely check out that video if you haven't already. We're going to kind of continue down that slope today, but we're specifically going to talk about buffer layouts. And when I say buffer layouts, I mean I'm really talking about vertex buffer layouts, okay? We touched on this. I mean, we've touched on this on my channel just in general because of course you can't really render anything without having to deal with vertex buffer layouts. I think I have a video specifically about that in the OpenGL series. I'll try and link it up there. Definitely check that out if you haven't already. And in general, if you're not familiar with the OpenGL series, I would just take a look at pretty much all of it because that's really going to help you out with what we're kind of building here at this moment in Hazel. And also, I'm going to continue that OpenGL series probably next week, probably throughout this kind of next week, because it's going to be really important in kind of taking a deeper look at some of these concepts that we're learning here in the Game Engine series. So anyway, today we're going to talk about buffer layouts. So what does that mean? Why do we need them? What do they do? And how do we write them in a way that is both abstract and works for every render API, but also is actually kind of easy for us to use because that's kind of what I'm all about, right? I want the code that we write on the client side, the code that we actually write like inside our game kind of project, right? Or inside our renderer to just be beautiful. That's kind of what I go for. That's what I aim for, right? And it's actually getting dark outside because I left this video pretty late today. I was just planning it and just making sure that I had everything that I wanted to say figured out because I really want to do this well. This specific episode, well, all videos really, come on, but you know, this specific episode. So if it kind of gets dark, I'm sorry because it is like the sun's about to set in half an hour. Anyway, the point is, beautiful code, right? I think that's really important. I think that if the code that you're writing, if you design an API and the code that you're writing just looks disgusting or just is hard to do things with or isn't concise enough, that's an issue, right? Think about writing.
All my code looks disgusting the first time I write it. Then I go through and refactor.
Make really like nice kind of flowing sentences. That doesn't really sound nice. It's not good for the reader to read. And just apart from that, not just
I'm
like
bad
it's not nice. Aside from that, it's just not
coding.
like actually practical. It just
like
doesn't work.
get it working.
Right? Like the person might have to
then
read
we'll
your sentence
come back
or they might have to read a whole much more information that they otherwise would have to understand what it is you're trying to say in your English essay, right? And of course, English essays, you're probably going for a high word count anyway, so you might just reiterate stuff over and over again. But in code, that's really not the case usually. Like you actually are trying to be concise, right? And just in general, you want to use kind of grammar and sentences that both kind of sound nice, kind of in your essays, right? In your English essays, back to this. But also stuff that actually gets your point across very just concisely and just nicely, so that the person kind of wants to keep reading, and so that the person forms a good visual kind of mental image of what it is you're trying to do, and everything is just beautiful and everything just feels solid. That's what we want to achieve with all of the APIs in this engine, right? That is what we want to do. That's not easy to do, right? But because we're using a language like C++, it's extremely flexible, and it actually means that we can do a lot of what we're trying to do. And today, specifically with buffer layouts, I'm going to show you how there's many different ways of essentially doing the same thing. But I want to do it in a way that actually looks good. Like we're talking about a buffer layout. We should just be able to visualize the code and be like, I get everything, right? I get everything. Like we don't want some weird, weird kind of way of writing code for this buffer layout where it just doesn't make sense or it just requires us to really think about what it is we're defining. No, we want it just to be easy. We want it to just be really easy because if it is easy and if it is just so nice, right, and elegant, then apart from just looking good and us feeling good about ourselves and also other people dealing with this and being like, this is great, this is so easy, apart from that, it's also actually going to reduce the bugs in our code. Why? Because everything just makes sense. And if something is wrong, we can intuitively kind of just pick up on that. We don't need to just read the documentation and be like, yeah, I guess that's wrong. No, we can just see the errors right there because it's laid out in such a way where errors are obvious, okay? That's what we're going to talk about today. We're going to jump in and we're going to take a look at just the practical example of what we actually have, as well as talk about what it is we're trying to kind of create. And I think that that's really important when you kind of talk about any kind of API that you want to design or any kind of complex concept. It's what is this actually doing, right? And with vertex buffer layout specifically, it's very simple. You know, what we're doing is we're actually telling OpenGL this byte array of data, what's in it? How is it broken down? You know, how many elements are there? How many, like, what are the elements? You know, is this a 3-component vector of floats, right? Or is it just 3 separate floats? You know, is this a 4 kind of component color? How is it specified? Is it just, maybe it's just an unsigned integer, you know, or maybe it's 4 separate floats, or something like that, right? It could be just absolutely anything. Like, if it's just a binary blob of data, which is what our vertex buffer actually takes in and uploads into the GPU, we need some way to actually describe the layout of that data, which again means, you know, the first 4 bytes might be a float, the second 4 bytes might be another float, and then the third 4 bytes might be another float. That's 3 floats in a row. That's our 3-component vector that describes our vertex position, stuff like that. That's what we're trying to achieve. Let's try and do it in an elegant way. Let's jump in and take a look at a practical example, and we'll see how we go. Okay, so last time I had this triangle. Today we're going to basically aim to achieve the same thing, but a lot more elegantly. And specifically, we're also going to maybe jam in some other vertex attributes for fun, just to kind of see how they work. Maybe we'll just throw in a vertex color or something like that. Let's just close this. So currently we are actually specifying a buffer layout, right? If we weren't, we wouldn't see anything on the screen. And that's this right here. Okay, these 2 lines of code. What this is saying is inside our vertex buffer, this one that we're creating, we have at index 0 3 floats, right? They're not normalized. The stride between each vertex is that size, so 3 floats, 12 bytes, and the offset of this particular element is nothing. Right? Now, I don't really want to discuss how this works too much because I do have an OpenGL video about it, and as I said, the sun is setting, and I have like other stuff to do with my life, and I don't want to sit here for 2 hours just reiterating, wasting your time, just describing everything that I already have already. So definitely check out that video. That, I don't know, like this is like, in my opinion, quite simple to understand. So if you don't understand this particular line of code, make sure you check out that video because I'm not going to really talk about it too much, I think, in this episode. So a few things that I actually want to point out with this particular line of code is, I guess, the linkages of it. So what it's referring to, what it's linked to, what it corresponds to, right? So vertex attributes specifically are actually stored in the vertex array, not the vertex buffer. Now they describe data in a vertex buffer. However, a vertex array is kind of the parent type, if you will. And a vertex array can contain multiple buffers, right? We can actually interleave our buffers and have, you know, just in this one vertice, like, right, in this one kind of vertices array, we can just add, you know, we want a vertex color or a vertex normal or something, we can actually just add it, like, just bam, like that, you know? And that way, you know, every single vertex that we have is kind of going to contain, in this case, maybe both a position and a normal, right? Or the other thing we could do is kind of just not interleave it, so not have any of this, right? But then just make another kind of array here, right? Another float array, which just had vertex normals. And then we can actually upload that into a separate vertex buffer. We can create another vertex buffer just for the normals, and then another one for the colors, and then another one for, you get the point, right? So because of that, OpenGL doesn't really care how you do that. You can interleave all your data and have one big fat vertex buffer, which is pretty much what you want, like 99% of the case, by the way. Or you can split up your vertex buffers into separate kind of actual vertex buffers and separate buffers of memory, and then upload them individually. It doesn't matter because this stays the same, right? It's just you happen to bind different vertex buffers at certain times when you actually describe your vertex array. And we'll kind of maybe talk about that in the next episode.
Kind of like eating. It's all good, get chewed up and dumped in your stomach
anyway. What I want you to know is that this particular binding, this kind of, I'm enabling a vertex strip array and specifying the layout of my buffer, that is stored in a vertex array. If I bind another vertex buffer or something like it, I don't need to redefine this. All I need to do is this state gets saved into my vertex array. If I want to recall it for rendering, I just simply bind my vertex array again, and it's done, okay? The second piece of information is that this is directly tied to our shader, right? If we look at a shader, like we've specified one here, look at this, layout location equals 0, vec3, a position, right? That's this piece of data. 3-component vector, right? 3 floats, that's what a vec3 is, right? Not normalized, 3 times the size of floats, 12 bytes, again, the size of this type, index 0, layout equals 0, rather location equals 0, right? That is what that's tied in with. If we suddenly want to take in a normal, right, we put that in location 1, let's just go with the color in this case because it's a different type, a vec4, and this will be our kind of vertex color, right? What do? We duplicate this, right? We have it at index 1, and by the way, we also need to enable it. So enabling index 1, we have 4 floats, and then the rest is kind of the same, except this changes. Because that is, and this is wrong, by the way, sorry, this isn't the size of, this is the stride, so it's actually the size of each vertex, not the size of each element, right? So it's kind of the size between each vertex in the array. So if we have 3 vertices, it's the size of each full vertex, which will be the size of both the position and the color in this case, which would actually be 7 times size of float, and that would be the same for both of them. So this changes to this, right? And then the offset is the offset of this particular element, right, inside the buffer. So obviously this is a vec3, that's 12 bytes, 3 floats, right? 12 bytes, so the offset of this is going to be 12, so it's simply 12, right? And we just need to cast it to a const void pointer. Okay? Const. Okay, so that's kind of what we end up with. But you can see that it's directly tied to my shader. That's the kind of the point that I want to drive home right here, is it's tied to my shader, okay? And it's actually not really tied to shaders in OpenGL in the sense that there's no validation performed between that. In DirectX, it is absolutely performed, right? You cannot describe a vertex buffer until you've bound a shader, okay? So it's actually a bit different than how OpenGL works. Anyway, that's kind of my point. So because it's so heavily tied with my shader, what I actually want to kind of do for my buffer layout is I basically just want to be able to set a buffer layout onto a vertex buffer, right? Now I did just say that they're tied to vertex arrays. However, a layout describes a vertex, like a layout is specific to a vertex buffer. It describes the layout of an actual buffer of memory. So whilst OpenGL kind of stores the state in vertex array, in DirectX, that's specifically on vertex buffers, because there's no such thing as a vertex array in DirectX. But apart from that, it just makes more sense to us. So to us, it doesn't really matter that they're actually stored inside vertex arrays because we can still kind of work around that and store them wherever we like. It's just that in the end, under the hood, we'll make that differentiation when we need to. But the kind of surface level API should still set it onto the vertex buffer. Now, how do I describe this layout? Well, there's a lot of ways that you could do it, but I'm not going to waste your time and show you all the bad ways of doing it. I'll just show you a nice way of doing it, which is again what I'm talking about, where we want to kind of have an elegant visual representation of this. Wouldn't it be cool if, when we kind of describe this layout, we could somehow literally just have this kind of code like right here and just be like, you know, our layout equals kind of maybe put this in brackets. Our layout equals like that, right? Now I just realized I've got white spaces on, which we don't need. Wouldn't it be nice if we could just do something like that? Well, that's kind of what we're going to do. We're going to actually literally make it so that we can see a visual representation of our layout. So our goal is to have something that's maybe called a buffer layout, class, right, which is going to look like this, and then maybe what we'll have is each element is going to be kind of defined like this, okay? And we're going to achieve this by just using an initializer list and probably storing these elements in a vector. Now, we're not going to use vec3 or vec4. There's a GLM types in this case. Well, in here, they're obviously the GLSL types inside the OpenGL shading language. But what we're actually going to do is come up with some kind of enum that describes this data type. So we're essentially going to probably create like an enum class called like shader data type, which will be kind of our cross API, cross-platform way of just kind of defining each data type that is inside a shader. So like vec3, vec4, you know, float, int, that kind of stuff. So we'll probably use something called like float3 to describe a three-component thing. You know, vec3 is cool and all, but I kind of like float3. That's kind of the HLSL style way of doing things, and we are probably going to eventually switch to HLSL shaders. You can use vec3 if you want, because that's kind of tied to our math library in, like at the moment. But I'm just going to use float3 to describe a three-component float, right? Because it makes sense. And then we'll probably give it a name. Now, you don't really need to give it a name. It's useful to give it a name. Like in DirectX, we will have to supply some kind of string, as you'll find out in the future. But it's just nice to kind of give it a name just so that you know what this actually is. And if you want, you can actually call it the same thing, which is what I'm kind of doing in this case. So we might have that. Let's just get rid of this whole color thing. I mean, essentially you do the same thing with color though. You just make a like a float 4 and do all that, and that's not really nice, right? We'll get rid of color here. And we'll get rid of this stuff. Change this back to 3 floats. And we'll try and just render that triangle to begin with. Okay, so this is my layout, and I'll set my layout, and that's kind of it. That's actually how I want to define my layout. And you can see that it becomes really nice because suddenly if I have a layout that's full of like stuff that I need, you know, like, you know, we might have like texture coordinates or something. And you know, you have something like text coord and maybe normals, and then you might have like color or anything. It's just so easy to see the layout of this buffer, right? It's amazing. That's all I need to do. And obviously if I want to like have an array of things, or like, you know, if I want it to be normalized or not, I can maybe add a third parameter, but this is kind of what we're going for. So let's take a look at the magic to make this happen. So I'm going to define all this code inside the buffer file here, because it is to do with buffer layouts and all that stuff. So I'm going to make a class called buffer layout. Okay, and a buffer layout is essentially going to contain a vector of buffer elements. Okay, and these are going to be called elements. I'm immediately just going to give it a getter to return that, because we're going to need that. So get elements const, and that will return elements. Okay, and then these buffer elements are going to be another class. Actually, I'll call this a struct, buffer elements. And this is going to contain all of the stuff that we need to actually specify. Okay, so the first thing it will contain is a name. So std string name. I mean, in no particular order, we need the offset, we need the size, we need what else do we need? The count, I guess, because we can have like multiple of these. I'm not really sure if we need that, to be honest, because I'm just thinking about it. Like, we definitely need that for uniforms if we have like an array, but we don't generally. I think if we just have that shader data type, as I said, which is going to be the type of data, we'll kind of know the count of how many elements we have anyway. And we can always create helper functions to kind of convert between the two, right? So we'll maybe have the name, the type, the size, and then the offset. And I think that that should be enough, right? Now, the way that we constructed this over here was just by writing the type first, right? And then the actual name. So we can actually do that here as well. We just need to create a constructor that allows that kind of construction, all right? So I'll write const std string name and then shader data type. All right, and then over here, we will set everything. So name, we'll set to name. The type, we will set to type. Size, we'll set to 0. Size we can calculate pretty much immediately, I think, because that's just the size of the type. So we probably don't need to set that, although we can here as a default. And then offset we'll set to 0. Offset we can really only calculate once we have context. So offset is going to be the offset of this element inside our layout. So obviously, to calculate the offset, we need to be aware of all the elements in there. Because if this is like the second element, its offset is going to be the size of the first element, right? Because that's how much into the buffer it is. So we can't really calculate that just yet. But we can calculate the size, so we might do that. Anyway, enum class shader data type. Right, and we can make this like, I mean, if you wanted to, you can make this like a UN8T or something just tiny, because it doesn't really need to be very big. It doesn't really matter, you know. I'm not one to just, like, this isn't gonna be serialized. This is not like, maybe if it comes down to us trying to really pack this data in tightly, we can do that in the future. But you don't need to in the, like, the time being. So we'll have none, we'll have float 2, we'll have float 3, we'll have float 4, we'll have, I guess we can do like mat3, mat4. This is not just gonna describe attributes, by the way, it can describe everything. We'll have int 2, int 3, int 4. Yeah, that's probably good enough. We might have a struct or something for like uniforms. We'll cross that bridge when we get there. Okay, that looks pretty good to me. That's a good like basic type. We can have booleans as well. Maybe I'll just write bool at the end here. Okay, that's pretty good, right? So that describes all of our types. Now, two things I'm concerned about is the size and also the offset, which we can calculate in a minute. So what we can do is create some kind of function, obviously, that converts between this kind of shader data type and an actual size. So what we can do is just create a static uint32t shader data, we can just do shader data type size, I guess. Shader data type size, shader data type, and then this will simply, I'll let it easy into the jam because I can't type it.
Yay, I'm not the only one who misses letters.
That goes between
keyboard
the
type.
No, type that we have.
I'm not typing what you just typed.
In the float. And in this case, it just kind of, I don't know, let's just go 3, 4 for now. This just returns the size of it. So a float is 4 bytes, so it's going to return that much. And we'll also kind of do the same for pretty much everything else. So a float 2, 3, 4, mat 3, mat 4. I'm going to try and be comprehensive. Usually I like adding these things as I go just because this just takes a bunch of time and makes the video more complicated, but I'll do it at least for this for now because it shouldn't take too much time. All right, I think that's it. So all of these, right? We can just align these a bit. Okay. So float 2 is going to be 4 times 2. Float 3 is going to be times 3 times 4, right? A mat 3 is going to be times 3 times 3, right? Because it's a 3 by 3 matrix. A float 4 is going to be the same but 4 by 4 matrix. And int's going to be 4, and int is going to be, and int 2 is going to be that. that. You guys gonna get the point. And then we'll probably, I'm not sure, it might be 1 by, it might be 4. We'll see about that, but we'll just leave it as 1 for now. And obviously we'll return 0 if we have nothing, and also we should definitely assert here. Core assert, false, unknown shader data type. Okay, and we don't need to print out the type because that'll just break here and we can just inspect it using the debugger ourselves. Okay, there we go. That's everything. Hopefully I didn't make any mistakes. I was kind of hasteful here. But now we can actually see what the type of each piece of data is. Right now this is in buffer. Remember, when we actually move this into shaders and have more stuff, we'll deal with that kind of then. Okay, cool, right? So what we want to do now is actually calculate that size, right? So right here in size, we can already just call shader data type size and then pass in the type, all right? And then we have that, beautiful. Now, and this is just buffer element, of course, not buffer elements. When we create a buffer.
Alrighty, folks, I am going to end it here, but fear not, I shall return later on this evening with the misses. Let me get them up there. Of course, we will be doing our nightly Fortnite journey. Until then, have a great rest of your day and stay safe. Thanks for watching. Peace. Ah!